We start our today's lecture, and as promised, today I'm going to discuss the construction of scattering amplitude and the important physical quantity which is called cross-section. So in the absence of interactions, a state of a system is not changed. And in this case, the corresponding S-matrix operator is simply the unit operator. Well, this is clear. And it is convenient to single out this operator from the S-matrix so that the rest would then describe the effect of interactions. In other words, we write our S-matrix as an operator in the following form: identity operator plus I multiplied by another operator, where this T is called T operator. And so please do not misuse this quantity with the time ordering. So it's not a time ordering that we discussed in the last lecture. So it's just an operator which is called a T operator, following the tradition in non-relativistic quantum mechanics. And also following the same tradition, people put in front of this T operator an imaginary unit I. Now, evaluating the S-matrix element between two states, say initial state I, initial state, and the final state, which I denote by F, we obtain the corresponding S-matrix element, so F S I. And if we write it by substituting this decomposition of S-matrix, we would get then F I, that's what comes from the identity operator, plus I F T operator I. Now, this can be further written in the following form. So Fi plus I, and then from this matrix element of the T operator, one normally pulls out the four-dimensional delta function, which encodes the conservation law of energy and momentum. So K final minus K initial, where K final here is the total momentum in the final state, and K in is the total momentum in initial state. And then one gets a quantity which I denote as AFI. This quantity is called scattering amplitude. So upon you pulled out the delta function, what is left over is called a scattering amplitude. And this is the quantity of utmost importance in scattering theory. So scattering amplitude. Of course, defined in this way, the scattering amplitude depends on the normalization of external states. And you see from this formula that the physical dimension of this scattering amplitude is the same as the dimension of this scalar product offset by the dimension of the delta function that implements the conservation of energy and momentum. Next, one defines a quantity which is called a transition probability. A transition probability. denoted by WFI, transition probability between states I and F, which is essentially due to non-trivial interactions, and it is defined in the following way. So WFI is the square of the matrix element of our T operator between initial and the final state, divided by the normalization, of final state and an initial state. So written in this way, this transition probability, or defined in this way, this transition probability does not depend on normalizations of the initial and final states. Now, being defined in this way, it is clear that there is a problem with this definition, because the matrix element of T between initial and the final states contains this delta function. And so taking the modulus squared of this matrix element leads to the appearance of a square of delta function, which is undefined quantity. And to understand how to treat this problem of appearance of the square of delta function, it is instructive to consider the scattering process in a very large but finite volume. So to understand how to treat this delta function properly, one needs to go to the finite volume. So scattering in a large but finite volume. Let's denote this volume by letter V, and the time interval during which we observe the scattering process we denote by T capital. So T capital here is not time-ordered product, it's just a time interval. Now consider the Fourier expansion of the delta function kf minus k in. And this is the 4 integral d for x divided by 2 pi in the power 4 exponential I kf minus k in, right? Now, we have already one delta function. And so in the second delta function, in its Fourier expansion, then we can just identify kf with k in. This is a condition that would be the condition imposed by the presence of already one delta function. And therefore, the second delta function, then in the finite volume, it gets replaced by integral d for x, 2 pi in the power 4. And since kf is set to be equal to k in by the first delta function, simply then we are left with this integral, which in the finite volume gives the contribution c speed of light v multiplied by t. So ct is just an integral of dx0 divided by 2 pi in the power 4. So this is a way how in scattering theory one would like to treat the product of these two delta functions, which from mathematical point of view a priori has no meaning. On the other hand, if you consider the scattering in the finite volume, then you naturally treat one delta function as conservation law of the energy and momentum, while the second delta function goes into the 4-dimensional volume in which the scattering process is taking place. In fact, in the finite volume, you have to make further modifications. In particular, you have to consider different normalization of states in the asymptotic Fock space. Namely, for K1 and so on Kn, which is a state in the Fock space, we have the following scalar product, or let's consider in this case the scalar product of a state with itself, which simply means the square of the norm of the state. And in the finite volume, this is given by the following expression: n factorial 2 omega k1 and so on 2 omega kn multiplied with v volume in the power n. Volume in the power n. This formula can be justified by the fact that in the limit of infinite volume, this formula goes into the standard norm, which in this case should be, of course, written a bit different. So one has to consider not the norm, but rather the scalar product of states with different case. And then on the right-hand side, you will have the corresponding delta functions, signifying the fact that you are considering an asymptotic state belonging to the asymptotic Fock space. Now, let me not for the moment to dwell much on this normalization issue, and just continue with saying that the transition probability for the scattering initial state into the final state depends on time. You see, it's explicitly now depends on time. And you can introduce the notion of probability per unit time in a large but finite volume. So probability of transition initial state to a final state in finite volume V per unit time. It is defined in the following way. Let's write it as this curly omega fi, and it is then written by 2 pi in the power 8. One delta function we leave to represent the conservation of momentum and energy, as discussed. Then there will be modulus of the amplitude, scattering amplitude squared, and then contribution from normalization factors, namely first from the delta function, second delta function, which is CV divided by 2 pi in the power 4, right? That is this factor here where we divided, where we taken time away because we are considering the probability per unit time. So there is no t anymore there. And then there is a prefactor which comes from the normalization of our states in a finite volume, and this 2 omega, say, on kj multiplied by v. And then the product goes over all initial and final states. So I denote this in this way. It means the product of over all initial and final states. Okay, this is what is called transition probability per unit time in a large but finite volume.
I'm sorry, could you please explain what does the product over all initial and final states means? You mean all pairs, or you mean
No, you have a certain number of initial momenta described by K1 and so on, Kn. And then you have a certain number of outgoing momenta, particles with outgoing momenta, which define what you mean by final state. So let's say initial state is a state in the Fock space, which correspond to, say, n particles with momenta K1 and so on, Kn. And then there is a final state, which is described, say, by momenta. Let's say, write this as P1 and so on, Pm. And then here you have a product of omega depending on Kj, where Kj runs all the set of Ks and all the set of Ps. That's what means all initial and final states.
Oh, it's
all initial and final states. That means
it's a concatenation.
Yes, it's indeed it's a union of initial and the final momenta, and so Kj here, index j, is running over all initial and all final momenta. In other words, you are taking a product of this factor 1 divided by 2 omega on Kjv over all particles which take part in the scattering process. And this factor arises from normalizations from these prefactors here, from these two prefactors, FF, II, and in the finite volume, these quantities are finite, and they are represented by the contribution of this factor here. Now, I'm going to explain the further important quantity which naturally appear in this formula, which is called Lorentz invariant phase space measure. In the large volume, the limit of this quantity omega phi I is actually not so well defined, especially if you want to take v to infinity. If you want to send v to infinity, then we would have the problem with this expression. On the other hand, since the scattering process is such that initial and final states belong to the continuous spectrum, not to the discrete one, but to the continuous spectrum, because asymptotically you are describing free particles, and free particles belong to the continuous spectrum of the Hamiltonian, then the practical interest lies in determination of the probability of finding momenta Kj of initial and final particles in the infinitesimal interval between Kj and Kj plus delta Kj, dkj, where dkj is a small change, or in the infinitesimal description, the differential of Kj. So in other words, for free particles, the asymptotic momenta are continuous and they are distributed continuously, and therefore we are interested not in finding just individual momenta Kj, but we are interested in registering by our detectors the particles which have momenta in a certain small range, lying, say, between Kj and Kj plus dkj. Okay, that's an important a point which align with the actual experimental observations where our detectors, our devices, will be fixing the particles not with an individual momenta, but with momenta line in between within the certain small interval. And that's, of course, is related to the resolution of our devices which register the particles. So somehow we have to adjust this quantity as a transition probability per unit time to the fact that we are interested in finding the final particles in the small interval between within kj and kj plus dkj. Okay, so that's the next important point we have to implement in our formula. Now, in the final state, momenta, of course, must satisfy the conservation law. So sum of this kj should be k final, and this k final, the total momentum in the final state, of course, must be still equal to the total momentum in the initial state. The number of states in the momentum space is product of dkj over all final particles. And since we are considering the contribution of this momenta in the phase space, then the contribution in the momentum space will be, as I'm writing, so product of the all final states of these differentials dkj. And what concerns configuration space, then this reduces to the volume V. And so the contribution to the measure, or measure, if you wish, in the momentums in the phase space is a product of the measure in the momentum space, which is this dkj multiplied by volume factor divided by 2 pi cube, and this is product over all final states. So this is, let's say, measure with which we have to weight our differential probability, and weighting our weighting our transition probability with this measure factor defines what is called differential probability. Not differential because it will be now dependent on this differentials dkj. Differential probability is a quantity which is defined in the following way. So it's denoted by d omega fi, and this is 2 pi in the power 4 delta function kf minus k initial square of the scattering amplitude. So scattering amplitude modulus squared. Then CV, this is a factor left from the second delta function. Then there is a product over all initial states. Now I split the product over all initial states. So 1 divided by V factor 2 omega on Ki. And then there is a product over all final states. And in the final states, because of the presence of this volume coming from the configuration space measure, the factors of V cancel with the factor of V which are coming from the final states. And therefore here you will be left over with just dkj divided by 2 pi cube 2 omega on kj. So that removes from consideration the factors of V which are associated to the final particles. But on the other hand, it introduces these differentials dkj and defines this quantity differential probability.
Professor, can you explain this point again? How V is cancelling?
That's because there is a contribution from the measure in the configuration space. Since nothing depends on coordinates, the measure in the configuration space will come just with a factor of volume. So volume appears here as an integral, if you wish, d3x as an integration over d3x. And this is a contribution from the configuration space measure, while dkj, this will be a contribution coming from the momentum measure in the momentum space. So altogether, the measure comes as a product over all final states of the factors v multiplied by delta kj for every outgoing particle, for every outgoing momentum. Then we take our transition amplitude and we multiply it with this measure factor. And then these in the measure factor, let me do it with red pen, these factors in the final states cancel factors of V, which correspond to the contribution of final states. For the initial states, they will be there still, and this is what you see here. So these factors of volume associated to initial states, they stay, while the factors which correspond to final states, outgoing states, they exactly canceled, and you are left just with the differentials of momenta of the outgoing particles. Okay, that is what I mean by this cancellation of volume factors.
Okay, so is there some need also to remove volume for the initial?
Yes, because
momentum?
at the end of the day, you are interested in scattering in the infinite volume. And so factors of volume somehow in the quantities which you measure experimentally, they all should cancel. Otherwise, you cannot take the limit to the infinite volume. And the infinite volume is, of course, a good approximation to what happens in practice, to what happens in experiment. That's why it is important to be able to take the factors of volume out in the final formula, which you need to compare to the results of the experiment. Okay, so we have not yet finished. So this differential probability is not yet the quantity you want to compute with experiment, is not yet what you want.
Professor,
yeah,
I want
sure.
to ask you, in this measure you define, why we don't consider, why this measure doesn't consider the nature of the particles involved, like they are bosons or fermions? Because I was thinking that for bosons we should have greater number, but I see it's the same, where it's taken into account that we have bosons and fermions.
Look, we can scatter bosons and we can scatter fermions. So I will come to this a little bit later. Information on the particular scattering process is not sitting in these measure factors. Information about the scattering process itself, physical scattering process, it means information about local interactions of particles sits in this quantity, scattering amplitude. So this is where the particular Lagrangian is important. This is what defines the actual scattering of particles. And these factors, which I'm here decorating, this scattering amplitude, they are responsible, for instance, for such a thing as a conservation of initial and the final momenta, so conservation of energy and momentum in the scattering process, and then the quantities which are related to the way we would like to measure, we would like to perceive these quantities in our devices. That's why here there appears such factors related to the phase space measure of, say, outgoing particles. But about the incoming particles, I will also say something, but a little bit later.
Professor,
Okay,
but this is still for the classical particles, right? Or no?
No, because scattering amplitude is a quantum quantity. It's governed by the laws of quantum field theory. So that's of course quantum mechanical quantity here.
So, but if like, for example, if you have some particles like fermions or bosons, then shouldn't we have Bose-Einstein or Fermi-Dirac function involved?
Of course, we do have that, but as as I'm saying, well, there are two things which you need to take into account. Yeah, I'm a little bit simplifying this discussion because in reality, you also need to add in front of this differential probability, differential transition amplitude, you need to add a certain prefactor which takes into account the presence of the identical particles. But let me not to complicate the things, because this formula is already quite complicated to understand. As I'm saying, mostly the information of what you scatter and how you scatter bosons, fermions, whatever particles, sits in this amplitude. So later on, maybe even today, I will give you a concrete example how to compute the scattering amplitude, say in quantum electrodynamics, which involves both bosons and fermions. And so what I'm saying is that information about what you scatter sits in this quantity called scattering amplitude, this AFI. And the rest in this formula is a decoration which takes into account the phase space measure, which is important for observations, as well as a delta function, which is related to the conservation law of energy and momentum. Okay, that's how it looks like. Now, this differential probability can be rewritten, can be presented in a slightly different form. I take first this scattering amplitude, then there is a volume factor CV, then I will single out the product over initial states, initial states of the factor 1 V 2 omega on K initial, and then I will take together the delta function describing the conservation law of energy and momentum, and the product of over all final states of these differentials dkj divided by 2 pi cube 2 omega on kj. I'll just recombine the terms because the expression here in this bracket define the quantity which is called Lorentz invariant phase space measure. That's the standard terminology for this quantity. It's denoted by D with abbreviation LIPS, Lorentz invariant phase space measure, DLIPS. And this DLIPS is this quantity here, 2 pi 4 delta function K final minus K initial, and then product over all final states, dkj 2 pi cube 2 omega kj. So this is Lorentz invariant phase space measure. Why it is Lorentz invariant? That is because the delta function kf minus k in is a Lorentz invariant, and this combination of the differential dkj divided by omega kj is also Lorentz invariant. And the fact that, that it's Lorentz invariant, I think I mentioned in the first part of this course. You can also look at my lectures where it is proved that this quantity dk divided by omega on k is a Lorentz invariant combination. So it does not depend on the Lorentz frame. And sometimes people call it Lorentz invariant measure, NF Lorentz invariant measure, where NF means is a number which is the number of particles in the final state. So the number of outgoing particles. So this is relativistic density of final states, relativistic density in the phase space of final states, and it's called NF Lorentz invariant phase space measure. So before I will go on with the general theory, I would like to consider a physically very compelling example of the two-body phase space measure. So this is our example. To have more intuition, to develop more intuition with these quantities here is to consider two-body, the simplest one, two-body phase space measure, which is of course very important because appearance of two particles as a result of scattering is a very probable event, and therefore two-body phase space measure, of course, plays an important role in considering the scattering process, and that's very natural that we consider it as an example which illustrates how this quantity d-lips looks like and how to compute it. So two-body phase space measure means that in the final state, we have two particles. And let's associate with these particles, let's say masses. Let's give these particles masses, which I denote as m.
I'm sorry. And
yeah,
when we compute transition amplitudes, we suppose when they normalize that, as far as I can understand, that every initial state transitions into some final state. But what if we have some bound states as well?
Then it becomes more complicated. Then it becomes more complicated, and that situation I don't consider here. I think everything now will be determined by this quantity, which is called transition probability. If there is a bound state and the initial state is a scattering state, then the transition probability is 0, and we will not get contribution from these states.
And we get non-zero transition probability to both a bound state and an asymptotic state.
The question is, what do you mean by, in principle, there is no transition probability because this is not a scattering process. If you have a bound state, then the bound state lies in a different part, belongs to the different part of the Hilbert space. And in the lecture which I gave last time, which was devoted to the foundations of scattering theory, I explain the assumption of asymptotic completeness of the Hilbert space, which means essentially that the Hilbert space is divided into two parts. One part describes, one part corresponds to bound states, and another part corresponds to scattering states. So as matrix as a whole, this quantity is well defined on the whole Hilbert space, because any state in the Hilbert space can serve as an initial or a final state. If you would like, how to say, to get more intuition, I advise you to look at this lecture, which describes foundation of scattering theory again. And you will see there that the S matrix is constructed in such a state, then this question about scattering of bound states with, say, asymptotic states simply does not arise. It's not, I mean, the very definition of how S matrix operates removes this question from its appearance. Let me put this way.
Oh, okay, I'll look again.
Yeah, look again. So here the important fact is that the actual scattering states, they constitute only the part of the Hilbert space. But on the other hand, any state in the Hilbert space gives rise to in or out asymptote for the scattering process. And this matrix operates on the whole Hilbert space because any state in the Hilbert space gives rise to in or out asymptote. And this matrix is unitary, so it's a well-defined operator on the full Hilbert space. And this initial and final states, they belong to the continuous spectrum. They are in a way describe or correspond to scattering states. So those states which are going to scatter, which will be scattered. Okay, so two-body phase space measure. And we assume that in the final state, we will have two particles with masses m3 squared and m4 squared. And according to the definition of d-ellipse, so Lorentz invariant phase space measure, we can write that d-ellipse for this case is dk3 divided by the corresponding factor, and then dk4 divided by its factor, 2 omega and k4. And then there is this delta function, which I write now, which I split in the, on a delta function representing conservation of energy. So K03 plus K04 minus K0. and the delta function which represents a conservation of momentum in the scattering process, K3 plus K4 minus K, where K0 and K4 are energy and momentum is a sum of, so K as a whole, so K is K0 and K is the sum of momenta of incoming particles. Incoming particles. So this is all, this is what I denote before as K in. So that's the same quantity, which I, for simplicity, now simply denote as K. Sum of momenta of incoming particles. So further simplification of this quantity comes from the fact that you have this delta function here. And you can integrate out by using this delta function. For instance, the momentum K4. Because you have this delta function, you integrate it out. So K4 becomes now dependent. And it turns out to be K, say, minus K3. K minus K3. And d-ellipse then can be rewritten in this way. So d-ellipse becomes 1/2 pi. If I take into account also the presence of the speed of light, because I would like to pass from omega to the energy description to describe, to replace the omega by the corresponding K0. So I can write it as a 1 divided by 2 pi c squared dk3 divided by 4 times. So this is 2 by 2 gives me 4. 4 times multiplied with K03, K04. And then there is a delta function, which gives me conservation of energy in the scattering process. And so K4 now is not independent. K4 is given by the difference K minus K3. K03, energy of the particle with mass m3 is given by K3 squared plus m3 squared, right? So that's dispersion relation, which describes the energy of the particle where its momentum. And analogously, we have a similar formula for energy of the particle with a mass m4. So this is K4 squared plus m4 squared. But as we said, K4 is not actually independent variable. So it is given by K minus K3 squared plus M4 squared, right? Now this delta function here is telling us that K0 is equal to K30 plus K40. And K30 and K40 are given by this formula. So if you substitute these expressions, we get the following equation, which is the same as the result of implementation of conservation of energy and momentum, right? Gives us this formula. And this formula actually you can consider as a constraint on the possible values of K3. Constraint on K3, which comes from the conservation of energy and momentum, right? That's simply what is written down here is a formula which describes conservation of energy and momentum. This comes from the conservation of energy, of momentum, and then the equation itself, sum of these two square roots equal to K0, is a conservation of energy. Nothing more than that. Now, to determine actually, to find what is the condition on K3 implied by this equation, it is convenient to come to the spherical coordinate system, introduce the spherical coordinates for K3, and write K3 in the following form. So differential delta K3 in the spherical coordinates will read as, say, rho squared d rho d omega, whereby rho I denote the modulus of K3, and d omega is a solid angle. As usual, d omega will be sine theta d theta d phi. D theta d phi. So this is solid angle, and K3 is the modulus of K3, and this is how differential looks like in the standard spherical coordinates, from Euclidean to spherical coordinates. I do transition from Euclidean to spherical coordinates for the vector K3. Then this delta function, which describes conservation of energy, I would like to treat as a function of this variable rho. And so I would like to rewrite it where the delta function, which looks like rho minus k with star, where k star I understand as a solution of the following equation, as a root of the equation K30 plus K40 minus K0 is equal to 0. So what I want to do, I want to make a change of variables in the delta function. And when you make this change of variables, you know how to do it. You need to take a delta function rho minus K star, where K star is a root of this equation. So K star is a root. And divided by the derivative of this function, which appears under the sign of delta function, over the variable rho evaluated at K star. So in other words, you need to take the derivative of K03 over d rho, modulus of derivative dk3 0 over d rho, plus delta K04 over d rho, and then substitute in this result rho equals to the root of this equation K03 plus K40 minus K0 is equal to 0. Then this is a change of variables in the delta function. So formula for the change of variables in delta function. Do you know this formula? Let me ask you if you know this formula. So what I'm applying here is the following change of variables. So delta function on any function of f on x is given by delta function x minus, say, x star, divided by modulus f prime on x at x equals to x star, where x star solves an equation, is the root of this equation. F on x star is equal to 0. That's the standard formula for the change of variables in the delta function.
Yes, we know that.
You know this.
Well, we know that we used it before in the Klein-Godin equations.
Yeah. So this is, of course, very well-known formula. in the theory of generalized functions, and that's what I'm implementing here, because at the end of the day I want to perform integration over rho, and let me then say that explicitly we have written down already this equation. This equation here is the same as an equation here. And if I rewrite it in terms of rho, this variable which we want to integrate out, then this equation will look as follows. So k3 squared is a rho squared plus m3 squared plus square root. And now this k minus k3 squared, I need to open up. So this is rho squared minus 2 modulus of k rho cosine theta. This is what I'm now writing down in an explicit way. Scalar product plus k squared. I remind that k is a total initial momentum plus m4 squared. And this must be equal to the total initial energy. Must be equal to k0. Okay, so now if you integrate out this delta function, the variable rho will be replaced by k star, where k star is the root of this equation. So k star is the root of this equation. So let me point this out explicitly. So k star is the root of this equation. And therefore, if I perform integration of this quantity d ellipse over rho, so I replace this dk3, as I said, rho squared d rho d omega. So integrating over rho will replace rho by k star. So d ellipse then becomes the ellipse takes the form k star squared d omega divided by, and now I take into account all the prefactors of 2, c squared, and then k03 as a function of k star, k04 as a function of k star. No, and finally, because of this change of variables, I have in the denominator these derivatives evaluated at rho equals to k star. This is how the ellipse look like after we perform an integration over rho. Any questions here? So let me pause for a moment. Just
Or is there in the beginning we have dk3 and dk4, and why dk4 just disappeared?
why disappeared? What disappeared?
Yeah, in the beginning, in the ellipse, we have dk3 and
K4 disappeared because we solve for it by using this delta function.
Yeah.
K04 now is this quantity here. K04 is given by this quantity here, right? Where now instead of K3, we have to substitute, and this is a quantity which I'm still keeping here as an expression being equal to the square root, where K3 should be then replaced, K3 squared should be then replaced by k star upon integration of this delta function. Here, you may replace, you need to replace actually modulus of k3 by k star. And this is what I'm writing here. So k03 is a function of k star and k04 is a function of k star.
Yes, but I mean dk4, the differential. I think there you're right.
We integrated over it. So this is dk4 together with delta function.
Yes.
Gets out because we integrate over it. We integrate over k4.
Ah, okay.
We integrate over it. So we integrated this delta function. That's why this delta function together with the differential, its integral is taken. So that's why this is this thing disappears totally. And dk3, we go to spherical coordinates and we integrate over the length of this vector k3, which becomes rho, which is the same as rho. And integrating out means that I have to replace the length of the vector k3 by k star, which is a root of this equation here. Right? And what will be left over is integration over angles, theta and phi. And this is still encoded in this solid angle measure, d omega.
Okay. Thank you.
Mm-hmm. Now, further simplification, if you want to simplify this formula further and write it even in a more tractable way, then you can go to a particular Lorentz frame. And since you know that d-ellipse is Lorentz invariant quantity, it does not matter in which frame you calculate it. So you can pick up a convenient Lorentz frame. And in particular, the convenient Lorentz frame is a frame which is related to the center of mass frame of incoming particles. In this frame, the momenta k, which is the total momenta of incoming particles, is equal to 0, right? That's the center of mass frame. The total momenta of particles is equal to 0. So you just find so you have the total momentum, and then you adjust your Lorentz frame in such a way that the total momentum of particles in this frame is equal to 0. That's what is called center of mass frame of incoming particles. Why this is convenient? That's convenient because this term in this equation in this frame just disappeared. You don't have it. And then you see that if you take dk03 over d rho plus dk04 over d rho, so what is k03? K03 is essentially this square root here. When you differentiate it over rho, you get 2 rho divided by 2 square root of rho squared plus m3 squared. So 2 cancel out, and you just get rho divided by k03, because k03 is the square root. So it's rho divided by k03. And analogously, for the same reason, you get for derivative of k04 over d rho. So you need to differentiate this expression over d rho. Clearly, you get the same thing, similar thing, like rho divided by k04, right? Again, you differentiate the square root over rho. You get rho in the numerator, k04 in the denominator. And this you write as rho, and then common denominator, k03 plus k04, sorry, divided by k03, k04, sorry, multiplied, you just get rho, And then K03 plus K04 is K0, right? Because of this conservation law. K03, K04. And this you need to compute in the substitution rho is equal to K star. So then the ellipse reduces to K star squared d omega 16 pi squared c squared. Let's have a look. So K0 you have here, depending on K star. Another K04 depending on K star. And then this modulus, so rho is positive and all the other quantities, they are energies, they are positive. So you have rho is K star. Multiply by K0. K0 is the total energy of the incoming particles in the center of mass frame divided by K03 on K star, K04 on K star, which is very nice because these terms just cancel out. And 1 power of K star also cancels out. K star here, but it's cancels out with 1 power, 1 power in the numerator. And therefore, in this frame, d ellipse takes a reasonably simple form. D ellipse, as computed in center of mass frame, takes the form K star d omega divided by 16 pi squared c squared K0. So K0 is just energy of the incoming particles in the center of mass frame. So the ellipse essentially reduces to the integration over the angles, and K star in the present construction in the center of mass frame is a solution of this equation here, is a solution of this equation here. And you can solve this equation for rho, and rho becomes a K star. In this case, you can do it very easily. You just take a square of this equation, isolate the roots, and you find for K star the following explicit answer. So the K star is just 1 divided by 2K0 square root K0 squared minus M3 plus M4 squared K0 squared minus M3 minus M4 squared. That's a result of solving this equation here. That's the result of solving this equation. Again, in the center of mass frame, you don't have this term. And you solve this equation with respect to rho, and solution you call K star. So the root of this equation. And then the root is given by this formula here. You can check me by solving this equation yourself to find this expression for K star. So this is how the ellipse looks like. Yeah.
So, but if we measure it in experiment, so shouldn't we consider theta here?
Should we consider what?
Theta angle.
Yeah. So the omega does depend on the angle. What is the?
No, in the center of mass frame we have not in theta goes away, right? 2 cos theta in one element.
It does not go away. This term goes away because K because K is equal to 0 in the center of mass. of incoming particles. K is 0. This is what is 0. Then the formula which you are left with, and this is also becomes 0. So this term also goes away. So what you get is just an equation for rho. So the equation which you have, which solution I'm presenting here, it looks like this: square root of rho squared plus m3 squared plus square root of rho squared plus m4 squared is equal to k0. This is how this equation looks like.
Okay, okay.
How you solve this equation? You square both sides of it, right? Then if you wish, you isolate again a square root which comes out from the product of these two roots and square it again. And then I think you get something like a b quadratic equation for the variable rho squared, and you solve it. And what I'm presenting here is a solution.
Right.
Mm-hmm. Yeah, to simplify an effort, you can just put it in Mathematica and just solve it by Mathematica. Let's see which did produce you this root here. And so this is how the ellipse effectively looks like. It's not so complicated formula for it we got. For the case of two particles, and I'm saying this is important because it is a primary relation to experiment. That's why it's good to know how this quantity is obtained. But this is not the end of the story, because I'm driving myself to the quantity which is called invariant cross-section. No, invariant means Lorentz invariant cross-section. A cross-section which value does not depend on the Lorentz frame in which you consider it. And to understand how this quantity is defined, we actually have to look at a little bit at the geometric setting of the scattering process. And typically, what happens in the scattering process is that you have a certain interaction region. And in this interaction region, you send on this interaction region where particles really collide, and there are processes of interactions between the particles mostly happen. You send on this region, the region of the collider where collisions happen, you send several beams of particles produced by accelerator. And in these beams, the particles have approximately the one and the same momentum. Say, for instance, in this red beam, my particles have approximately, say, momentum K1. Let me write here, say K1. Then you may send another beam in this interaction region, say, of green particles. And in this beam, they all will have approximately momenta, say, K2. And then this is not the end of the story. In general, you can send another beam, say, of some other particles with another momentum K3, with another momentum K3, and so on. So you send from accelerator, you send several beams. In the simplest situation, these are just two beams of particles sent to the collision region, interaction region, and then you register with the help of devices, various devices. You measure what gets out. What gets out, let me write this in red. What comes out from this interaction region after the particles collide. You have your detectors around, and you measure in these detectors the outgoing debris. And the quantity which I would like to measure in this scattering experiment is what is called differential cross-section. Now, of course, you may understand that the quantity which we defined so far contains also an information about our accelerators or accelerator, because accelerator produce our particles with a certain intensity, So, and by intensity, or another name for intensity in the context of particle acceleration is luminosity. Luminosity is a ability of accelerator to produce a certain number of colliding particles per unit cross area per unit time. And so this differential probability, which we have defined, of course, contains still information about our accelerator, about its luminosity. How many particles are produced per unit time, per unit cross area. So accelerator might produce particles with a very low rate, or it can produce particles with a very high rate. So in 1 second, it produces either 100 particles, or in 1 second it produces 100 particles, or it produces thousands of particles. And also the density, so how many particles are passing through a given cross-section, say, per second. And so what we need to do now, somehow we have to define this luminosity, and we have to exclude it from the differential probability. And this exclusion we define for us a quantity which is called differential cross-section. So at the end of the day, the differential cross-section is the following quantity. I denote it by d sigma fi. And this is differential probability, as we defined it above, divided by the luminosity. Luminosity. So once again, luminosity is a number of particles of colliding particles, particles produced by accelerator per unit cross area per unit cross area per unit time. That is a bit different of how we define this luminosity in quantum mechanics and quantum field theory. In fact, this formula which I'm writing here is quantum analog of the classical formula. And the classical formula for a scattering reads like this. dn is equal to L luminosity multiplied by d sigma, where d sigma is a differential cross-section, differential cross-section, and dn is a number of scattered particles entering the area d sigma. Number of scattering particles entering the area d sigma. And the proportionality coefficient between these two quantities is a luminosity. So the more powerful your accelerator, the more luminosity it has, and therefore the more particles, the more scattering particles enter the area d sigma. So from the classical point of view, or point of view even from quantum mechanics, usual quantum mechanics, say non-relativistic quantum mechanics, d sigma differential cross-section is a ratio of dn to luminosity of your accelerator. Here in quantum field theory, we define the differential cross-section by similar formula, where the role of dn is played by this differential probability d omega. Differential probability d omega. Now,
I have a question. What's the relation between the luminosity and the scanning amplitude?
Luminosity has nothing to do with the scattering amplitude. Luminosity is defined by the number of scattering events which happen, the intensity of scattering events. Roughly speaking, it depends of how many particles will find each other to collide. And if they collide, then the weight of this collision is weighted by the transition amplitude. But the transition amplitude is one quantity. It's determined by microscopic laws, by your Lagrangian. And luminosity is defined by such a quantity as density of the particles. Density of particles in the colliding beams. You see? That's exactly what I'm saying. So your accelerator produces particles with a certain density, with a certain intensity. And so this is in a way characteristic of your accelerator. It's not a characteristic related to the microscopic laws of how particles interact. It's rather related to your device, to your machine.
Okay, thank you.
Mm-hmm. So, in any case, what I want to say here, two comments. The comment number one is that differential cross-section has a physical dimension of area. This is clear. That's because luminosity is a number of colliding particles per unit cross area. And the words per unit cross area actually mean that differential cross-section will have a physical dimension of area. And it's both the same thing in the quantum mechanics and in the quantum field theory. The other thing which I want to mention is that the definition of luminosity does depend on the number of incoming beams. Of course, for the simplest but most relevant case of two-body collision, the luminosity gives rise to the Lorentz invariant cross-section, can be defined in the following way, which I describe now. But the point why I'm taking just two beams, this is because for two particles to collide, the probability is higher than to collide, to find themselves in a collision, 3, 4, and more particles, right? So the probability that two particles collide is higher than the probability that 3 particles simultaneously collide, or 4 particles simultaneously find each other to collide. That's why the events which involve just two beams of colliding particles have a high probability, and that's why it makes sense to consider this situation first. And this is the only thing which I do, because probably for this course, the most important thing to discuss is a two-particle collision events. Two-particle collision events. So if we assume that we have just two beams to collide, then we can define, we can construct the Lorentz cross invariant section in the following way. We can introduce what I call laboratory frame. Let's introduce what is called laboratory frame. Oops. Laboratory. And this laboratory frame, I denote the laboratory frame by letter L. Particles with initial momenta K2 will be at rest. So I find the Lorentz frame where particles with momentum K2, these ones, these green ones, are considered to be at rest. And so if they are at rest in this Lorentz frame, they play a role of a target. They are not moving in this frame, and so I consider them as a target. So particles with initial momenta K2, initial momentum K2, momentum K2 are in L, in laboratory frame, are in at rest. So they play the role of a target. And the particles in the beam K1, L, so particles in the laboratory frame, they will have momenta K1 laboratory. K1 laboratory is different from K1 because now I go to the frame, to the special Lorentz frame, where particles with initial momenta K2 are at rest. And so particles in the beam where they have initial momenta K1, now with respect to the laboratory frame, they have momentum K1L, and they collide on the target. So particles with K1 laboratory, they collide with particles making our target. And to understand how many events, how many collision events happen or may happen, we consider the volume V, which is a product of cross-section delta S by dx. So the picture is like this. Let me maybe draw the picture, which will appeal to your geometric intuition. So we have a certain cross area. Like this. So this will be our cross area delta S here. This will be delta X, the depth. And then in this volume, being delta S, delta X, we have our target particles. So they are sitting inside. I denote them as black particles. They are at rest. They are not moving. They constitute target. And on this target, with the momentum K1L, we have a flux of incoming particles, which I denote by red. And they are entering this volume, and they have a chance to collide with our black particles. So they get in and probably collide, probably find blue particles and collide. The probability to find the target particles in the volume V are, of course, proportional to the volume and the density, particle density. So this probability is, let me write it as ρ2, the density of particles in the second beam multiplied by this volume V, right? So this is, let's write probability to find target particles. Now, this quantity we have to multiply with the probability that an incoming particle passes the cross-section delta S of our target per time delta T. And in this way, we would get the number of potential colliding events. And so how to compute the number of the particles which have a chance to get in and collide? It is given by ρ1, the density of the particles of the first beam in the laboratory frame, multiplied by V1 L. This would be the velocity of the particles of the first beam multiplied by dt. So that makes for you dx, and then multiply by cross area. So this is probability for particles from the first beam, to enter the volume V. So this length here is V1 laboratory. So velocity of the first particles, or particles from the first beam, multiplied by delta T. Multiplied by the density of the first beam in the laboratory frame, density of particles in the first beam. And so the number of potential colliding events, the number of potential colliding events is then the product of these two probabilities. So ρ1L, V1L, delta S delta T, multiplied by ρ2 multiplied by V. So ρ2 is the density of particles of the second beam in the rest frame, and the frame where these particles constitute a target and do not move. All right. So luminosity then, as we said, is a ratio of n, the number of potential colliding events per unit cross area per unit time, which means that this quantity is then given by V1L, ρ1L, ρ2. No, we can write ρ2 as ρ2L, but we understand that this is density of the second beam where particles are forming targets, so they are at rest, multiplied by the volume V. This is luminosity. And now we can go to the definition of a differential cross-section. But at this point, I think it's reasonable to make a break, say 10 minutes. Let's have a little bit of a rest to think about this definition of luminosity, and come back in 10 minutes to define the Lorentz invariant cross section. Okay?
Okay, thank you.
Okay. Let's have
Okay,
a
thank
break.
you.
Let's have a break.